Okay, welcome back to my channel everyone. My name is Ansar, your helping hand, and in today's video we're going to be going through another IFoA question, exam paper question. And this question has quite a lot of moving parts. So it's predominantly has to do with well, most of the marks are actually about moment generating functions, but there is a bit of the central limit theorem in it as well, and also just kind of the relationships between different types of distributions. Okay, so this question comes from the 2010 September paper, and it's question 8. So as usual, I'll read the question through with you. You then pause the video, attempt it on your own, and then come back for the answers. Okay, so the question reads as follows. A certain type of claim amount in units of £1,000 is modeled as an exponential random variable with parameter lambda is equal to 1.25. An analyst is interested in S, the total of 10 such independent claim amounts. In particular, he wishes to calculate the probability that S exceeds 10,000. And then we've got all these questions. IA1 says that show using moment generating functions that S has a gamma distribution. IA2 asks you to show that using moment generating functions that 2.5S has a chi-squared distribution with 20 degrees of freedoms. IB says use the tables to calculate the required probability. IIA says specify an approximate normal distribution for S by applying the central limit theorem and use this to calculate an approximate value for the required probability. And then IB or IIB asks you to comment briefly on the use of this approximation and on the result. Okay, so that's the question, right? So go ahead and pause the video and attempt it by yourself and then come back for the answers. Okay, I'm assuming you attended the question, and now we're going to go through this particular question's answers. So for the first question, we have to show using moment generating functions that S has a gamma distribution. So before we kind of get to the question, as usual, it's always good to look at the information you've been given and define some notation. So we're going to say that our claim amount, or our ith claim amount, right, because I is going to go from 1 to 10, that has an exponential distribution. Now, this is important. There are different forms of specifying an exponential distribution and a gamma distribution. So here they're specifying an exponential distribution with a lambda parameter, and we have learned in our module that we use the exponential with a beta parameter, but it's not all that different. It's just that beta is 1 over lambda or lambda is 1 over beta, and the same thing applies to a gamma distribution. A gamma can either be described using an alpha and a beta or an alpha and a lambda. Here they're using the lambda parameter, but we've kind of been taught with the beta parameter, so I'm just going to write it in terms of beta. So Ci is equal to a exponential where beta is equal to 1 over lambda, and lambda is 1.25, which is 5 over 4, so beta is the inverse of that, which is 4.5. So these are individual claim amounts, right? And we have that C1, C2, all the way through to C10 are all independent, and they all have the same distribution, which is an exponential, an exponential with beta equals 4.5. Okay, so that's the first kind of notation thing that we have, and then we have to define S as the sum from I equals 1 to 10 of our CIs. Now, we can answer the first question. They say show using moment generating functions that S has a gamma distribution, right? So in order to show that, we would have to show that the moment generating function of S, right, of t, is equal to 1 minus beta t to the power of minus alpha. So if we can show that the moment generating function of S looks like this form, where we've got 1 minus a constant in front of t to the power of negative times a constant, then we've shown that S has a gamma distribution. Now, I'm not going to go through the entire kind of every single step, but the way this is going to work is, because we have an independent sum, the moment generating function of the sum is going to be equal to the product of the individual MGFs. So what that means is that the MGF of S as a function of t is the moment generating function of C, any one of our CI's, to the power of, well, it's the product of this multiplied, all of these CI's, their MGFs multiplied, but because we're going to have 10 MGFs of CI, or we're going to have the MGF of C1 multiplied by the MGF of C2 multiplied by the MGF of C3, all the way up to the MGF of C10. They all have the exact same MGF because they're IID, so we're just going to be multiplying the same thing 10 times, so that's the same thing as the individual thing to the power of 10. So now we need to know what the MGF of CI is, and because we have an exponential function, or an exponential distribution, we know that the MGF of CI as a function of t is going to be 1 minus beta, where beta is 4.5, t to the power of minus 1. Okay, so all of this is kind of recap from, well, theory that we've learned this semester, and you should have your textbook with you, and in an exam you would also have your list of formulas for all of these distributions. So we can then say, well, the MGF of S is just going to be 1 minus beta, which is 4.5t to the power of minus 1, and then we're raising that to a 10. So we've got 1 minus 4.5t to the power of minus 10. So there we've shown that the MGF of S is of the form 1 minus something t to the power of minus something. So therefore we've shown that S has a gamma distribution of 10, and our beta is 4.5. So we just match these up. So alpha over here is minus 10, or minus alpha is minus 10, so alpha is 10, and minus beta is minus 4.5, so beta is 4.5. Okay, so that's that's the first question. And just a quick side note, this would be true of any particular exponential, right? Whenever you take the sum of exponentials, you're going to get a gamma distribution where your a value is the number of exponentials you're taking, and the beta value is the same as the beta value for your individual exponentials. And that's just kind of not necessarily something that you need to know, but it's a useful result for your life, I guess. Okay, so that's IA1. So IA2 says that we have to show that 2.5 times S has a chi-squared distribution with 20 degrees of freedom. So we have to show that 2.5 times S, I'm going to try and write this very specifically so that you can see the difference between the 5 and the S's, that is a chi-squared distribution with 20 degrees of freedom. Now, it's important to know what the chi-squared distribution, what that MGF looks like. So if y is chi-squared with n degrees of freedom, then the moment generating function of y is going to be equal to 1 minus 2t to the power of negative n over 2. Okay, so now we just need to show that the MGF of this is equal to the MGF of that, where our n is replaced with a 20. So what we do is we say the MGF of 2.5s of t, right? Now we're using the definition. We're going to use the definition of MGFs because we don't really have a sum, so we can't use the MGF of a sum of independent random variables is the product of the MGFs. We can't use that trick, so we're going to have to kind of go from first principles, which is that this is e to the power of t multiplied by whatever our random variable is, and in this case our random variable is 2.5 times s, right? Now the important thing here is that these brackets, right, we can move them around, so this would be the same thing as t times 2.5 s, the expectation. And now when you look at this, right, if we look at our moment generating function of s, our moment generating function of s has a dummy variable here, t. We can plug t to be anything, right? And specifically, in this case, we're plugging in t to be t times 2.5. So this is the same thing as the MGF of s evaluated at 2.5t. And this is true also for any kind of MGF function that you have. Whenever you multiply it by a constant, whenever you multiply a random variable by a constant, the MGF is just equal to the MGF of the original random variable evaluated at that constant multiplied by t. So now we just need to know what the MGF of s is, but we've already worked that out. So it's 1 minus 4 over 5t. So that's going to be 1 minus 4 over 5. And now instead of t, we're putting 2.5t. And if you don't know, 2.5t is 5 over 2. So that's going to be 5 over 2t. And then to the power of 10, right? That's what our MGF of s is equal to. So we can simplify this a bit to be equal to 1 minus 5. Those 5's cancels. 4 divided by 2 is 2t. So we've got the 1 minus 2t so far. Now we just need the minus n over 2. And negative 10 is the same thing as minus 20 over 2. So therefore we have shown that 2.5s is a chi-square distribution with 20 degrees of freedom. Okay, so that's the first two questions. And then the last part of question I says, use the tables to calculate the required probability. So the required probability that we're trying to calculate is that S exceeds 10,000. But remember that 10,000 S, right, is the sum of claim amounts CI, where CI is exponential. But what's important is that our claim amount is in units of 1,000. So if we want to say that the claim amount, the sum of the claim amounts is greater than 10,000, we're trying to say that the sum of the CIs, because CIs are in thousands, is greater than 10. So our required, so let me just actually write what these, so this is IA1, right, and then this one over here is IA2, and now we're on IB. So the required probability that we're trying to calculate is that x, oh sorry, not x, no, where I got x from, that S, right, the sum of our claims amount, right, that is greater than 10,000, but as I said before, because we're talking about our random variables are in units of 1,000, this is the same thing, that S is greater than 10. Okay, so we could use a gamma distribution here. So we could do using a gamma distribution where we've got 10 and 4.5, but our tables don't really have gamma distributions of 10 and 4.5. They do have chi-squareds, so we can, write this instead as a chi-squared distribution or a chi-squared probability where we've got 2.5 times S is greater than 2.5 times 10, so that's going to be 25, where 2.5s is chi-squared with 20 degrees of freedom. Sorry. So now you could go and calculate this using the tables in the back of your book, but actually you'll realize that you can't because we don't have this particular value near we don't really have a 25 in that particular degrees of freedom line. So essentially, what's happening here is that you can't really use our tables that we've been given in our textbook to calculate this probability, but in the actuarial exam, they have different tables that probably you could have calculated this for. But you can also use, you can use Excel, you can use RStudio, you can use any statistical package that you can find to find this probability. And in that case, you don't really need to do this chi-square distribution. You can go straight from the gamma distribution because most statistical software that has a chi-squared will have a gamma distribution as well. So either way, the exact probability of this particular sum, or of this particular I'm going to say range, right? The exact probability is equal to 0.2014, and getting this particular probability is not really what's important. That's kind of, can you read a value out of a table, or can you type some things into Excel or RStudio or whatever statistical package you use. So that's the first part of the question. That's I, right? Now, obviously, in order to calculate that probability, we needed either a gamma table or a chi-square table. We needed some, statistical software. But for II, for the second part of the question, they say specify an approximate normal distribution for S by applying the central limit theorem and use this to calculate an approximate value for the required probability. So the way II works is that because we are now, instead of dealing with an exact probability, right, we're dealing with an approximate probability using the normal distribution. So we're using the central limit theorem. So just a quick recap of the central limit theorem in terms of the sum of random variables. So if I have x1, x2, ... xn are IID with mean mu and variance sigma squared, this should kind of be very recappy for everyone, right? So we can either define the central limit theorem in terms of the sample average and the limit of the sample average of that particular statistic. But in this case, we don't have a sample average, right? We have an S, where S is the sum, right? The total. So we want the CLT in terms of the total. And the way this works in terms of the total is that when we take the sum from I is equal to 1 to n of xi, this is approximately, and I'm going to say that approximately as n goes to infinity, a normal distribution where our mean is n times mu and our variance is n times sigma squared. Now, I've kind of, reiterated this in the past before, but we can't really take the sum of infinite things and get a finite value in this particular scenario. But what this approximation is actually saying is that not this approximation, but what this statement is actually saying is that as n gets larger and larger and larger, your sum will look like a normal distribution. So in this case, we don't have xi's, we have ci's, so we have c1, c2, all the way through to cn, or actually c10, not cn, because we know what the n is, are IID, exponentials with beta equaling 4.4 over 5, right? So we know what our mu is. Our mu is going to be, remember, mu is defined as the mean of an individual sample or individual observation. So our mu, or the mean of an exponential random variable, is just the beta parameter. So mu is going to be 4.5. Sorry, not 4.5. 4 over 5. And our variance sigma squared is just going to be beta squared. So that's going to be 16 over 25. So therefore our S value, which is equal to the sum of 1 through to 10 of our CIs, that has an approximately normal distribution, right? Where our mean is just going to be our mean of our the individual random variables, not the sum, multiplied by n. So that's going to be 10 times 4 over 5, which is just going to be 8. And 10 times our variance, which is going to be, if you work it out, is going to be 6.4. Okay, so that's the approximate normal distribution using the central limit theorem, or by using the central limit theorem. So now, where they ask us to calculate an approximate probability, right, we're trying to find the probability that our S is greater than 10, right? And because we have S as being approximately normal, this particular probability is very easy to calculate if we standardize everything. So we're going to take our S, subtract our mean, divide by our standard deviation, which is 6.4, is greater than, do the exact same thing on the other side, 10 minus 8 over root 6.4. And that is going to be equal to the probability that some z, where z is normal, right, that's what standardizing does, is greater than 0.791, and a lot more decimals. And then we just have to calculate this probability, which is a normal probability. You can go and look at your tables or whatever statistical software you use, and this is equal to 0.214. Okay, so this is our approximate probability that we got, 0.214, and our exact probability was 0.2014. So essentially, when we're asked to comment briefly on the use of this approximation on the result, we can say, well, our n value here, our n value was only equal to 10, which is quite small, right? Which is small for the CLT, right? Most of the time your CLT will see at least 30 samples, but instead we had a sample size of 10, and our probabilities, right, our probabilities were accurate, or our approximate probabilities were accurate to one significant digit. So if you need only one significant digit, then this approximation is great. If you need more significant digits, then using the approximation we used currently is not that great. But what we could do is just take more we could take more independent samples, so we could increase our sample size, and then our approximation would look better. Okay, so that's the end of this question. Please don't forget to like and subscribe, comment if you have any questions or requests, and yeah, I'll see you in the next video. Bye.